Okay, welcome to this lecture, which is covering Chapter 7, MRI, the basics, which is pulse sequences part 1, saturation, partial saturation, and inversion recovery for the UCSF course, Biomedical Imaging 201. As usual, I want to start things with a little bit of a distraction here, just show some interesting, things coming, particularly in the MRI research world. Since we're talking about contrast and inversion recovery, this is an example of a way that actually using some advanced reconstruction and acquisition techniques, you can create images that synthesize any of different inversion times, which we'll go into as a powerful contrast mechanism. And including, since this is heart imaging, you need to account for cardiac phase, so heart motion, and respiratory phase as well. So anyway, here's some links here to check out this really cool work. Okay, so the learning goals for this chapter are going to be for our 3 pulse sequences, we want to describe the contrast that they provide, draw a pulse sequence diagram, derive evolution of the net magnetization. In the pulse sequences, we're going to cover our saturation recovery, partial saturation recovery, and inversion recovery. And what you'll realize is we've actually covered the first 2. We're just putting a name to those here. So what is the process? What does saturation mean? What does this term mean in MRI? So what saturation refers to is we start with our net magnetization here along the z-axis. We apply 90-degree RF pulse, and we convert all this longitudinal magnetization to transverse magnetization. And at this point here, right, mz equals 0. So we're said the longitudinal magnetization is said to be saturated when we've converted it all to transverse, and there's none left. Now, building on this example, what does partial saturation mean? Well, start with the same scenario, the net magnetization along the z-axis. We're going to apply our 90-degree RF pulse. At this point, the magnetization is saturated. But then there's some amount of T1 recovery of the net magnetization. And maybe if we pick a sort of later time here, where T2 decay has occurred, we're left with net magnetization recovered, but not back to equilibrium. So in this case, now we're at equilibrium, 0, 0, m naught, and here we're at some, fraction of m naught, some constant a less than 1. And so in this case, we say it's to be partially saturated. So we saturated it, but it's basically getting unsaturated through the process of T1 recovery here. And then we progress on to unsaturated. So start off equilibrium, our 90-degree RF pulse. Magnetization is saturated. Then if we allow for time, and usually as we're going to call this is TR, that is much greater than T1, then magnetization here is back at equilibrium. And so we say this is unsaturated now when we've returned to full T1 recovery. So our saturation, partial saturation and saturation recovery pulse sequences are in fact simply the pulse sequence that you've already seen before. this repeated 90-degree RF pulses. And here I'm using this, again, this arrow shorthand notation to signify the effect of an RF pulse. And as we've done before, we can follow the magnetization from starting at equilibrium. In this case, the Z magnetization will get saturated at this point. Will be all converted into transverse magnetization. And then we'll see T2 decay, and we'll see T1 recovery. And so now we're back, and as I'm drawn it, this would be partial saturation. And we do another 90-degree pulse, convert this Z magnetization to transverse magnetization, T2 decay, and the same T1 recovery. And this continues in the steady state like this. And we know that once we're in this steady state here, that our signal is going to be proportional to m0 times 1 to e to the minus tr over t1. For tr is our separation of our RF pulses. And the distinction between this partial saturation and saturation recovery is really the duration of this TR time. And this is relative to T1, so I could draw it in this case of, we'll say we're looking at a different anatomy at shorter T1 times, where we have recovery back to m0. Then again have the same repeated pattern here. This time we'll have slightly higher transverse magnetization, higher signal, and this is what is referred to as saturation recovery. And this is where we return to the full recovery to the unsaturated state. So saturation recovery is going to be TR much longer than T1. Partial saturation would be, otherwise TRs that are, less than or equal to T1 about. Okay, so moving on to now the new pulse sequence in this chapter, and that's inversion recovery. And the pulse sequence looks something like this. It starts off with a 180-degree pulse. So I'm going to draw it a little bit larger here with some delay time Ti between the inversion recovery pulse and a 90-degree RF excitation. And then, as with the other saturation recovery, partial saturation recovery, this same pattern is going to be repeated. And the interval at which it's repeated, here I can label it either case, it's going to be TR. So again, we're going to have a repetition time. And so what does the inversion recovery part of this name come from? It comes from really this 180-degree pulse. And these are sometimes called inversion pulses. And the reason for that is they're going to take the net magnetization, it's pointing positive along the z-axis. We're going to rotate it 180 degrees, so it's pointing negative, or it's inverted along the z-axis. In our plot of mz here, that means we're going to go from starting at equilibrium positive along mz to 180 degrees flipped around, pointing negative. The other thing to note is that this type of RF pulse does not create any transverse magnetization. Okay, in this sequence, the 180-degree pulse does not create any transverse magnetization. And let me illustrate that down here below as well. So we're going to go from net magnetization, and the hair pointing along the positive z-axis, to net magnetization pointing along the negative z-axis. Okay. That's going to be the effect of this RF pulse. But now we're going to have some period of T1 recovery. And where we're going to relax back to equilibrium. And only going to see, since there's no transverse component, we're only going to see T1 recovery in this interval. So we can sketch this out as follows. Or this diagram down here, we've got T1 happening. So as I've drawn it, end up with some smaller transverse or smaller longitudinal magnetization. Then we're going to apply 90-degree pulse. So now it's going to behave like a 90-degree pulse in the saturation experiments, where the Z component is saturated. This is converted entirely into transverse magnetization. And then, once again, we have relaxation that occurs after the RF. And T2 decay. And then T1 recovery. Now, at another time here where things are going to just start repeating themselves. So we're back at, I'm going to end up oriented along the z-axis and have a 180-degree flip to the negative z-axis, and I'm going to repeat this process again. So we flip ourselves around in MZ, some amount of T1 recovery, no transverse magnetization, 90 degrees. Convert the longitudinal to transverse magnetization so we can get some signal here. and then do it again. All right, so let's put some values into this inversion recovery pulse sequence. Okay. So just gonna redraw here part of the pulse sequence. And we're going to assume that we're in the steady state, which actually occurs after the first time, we apply the sequence after the first PR. Okay, and we've got to do some algebra here and some bookkeeping to figure out what's going on. So we have sketching the last slide here. And you can label some of these things. I'm going to call this M1, call this M2, call this M3, and then I'm going to call this M4. And we know a bunch of stuff that's happening in this sequence. So first off, what the 180-degree pulse means is that M2 is the opposite or the negative of M1. This is flipping the inversion process. Then, during this next time interval, this value M3 is going to be M2. So this is our MZ0. If we go back to, and I'll repeat it up here, this general equation for T1. Okay, and I apologize, I seem to be drawing a little bit with my hand. So in this equation, M2 is the MZ0 in this time interval. And then this is going to have the total time interval is Ti. And we always have this term as well. And after M3, we do the 90-degree pulse, so we have saturation. So the equation for M4 is simply MZ0 is now 0 in this time interval, right? Here's MZ0, it's nothing. So we're just left with this second term. And we just got to keep a little track of our time interval here. Okay, and then what the steady state piece here means is that the magnetization is repeating the same pattern TR to TR. So this means that M4 is the same as M1. So putting these equations together, and we're going to target how we do this, noting that our signal is going to be proportional to M3, right? So it's whatever our Z magnetization is right before this 90-degree RF pulse. you can combine these four equations here and determine that M3 is equal to M0 1 minus 2 e Ti over T1 plus e to the minus Tr over T1. Okay, so that means our signal for inversion recovery is proportional to this same term here. Okay, so maybe I've led you here, but maybe you're having sort of a so what moment. Why do we go through this trouble of adding this extra inversion 180-degree pulse before we do our usual, what we've done before, 90-degree excitation? And there's one very compelling reason why we do that, and that's the fact that actually for a certain choice of TR and inversion times, we're going to get times where we've actually nulled, or we've actually canceled out the signals from various tissues. And so we use this as a method of, in fact, signal suppression by choosing carefully this inversion time and this TR time. So there's a couple of different ways that this is typically used. So again, we're choosing this to be sometimes called the null time, or TI null here. And there's often two flavors of this. One is what's referred to as STIR, or short time inversion recovery. And the purpose of this is to suppress signal from fat, which has a very short T1 compared to other tissues. Or the other major reason it's used is for flare, or fluid attenuated inversion recovery. And this is typically done to suppress fluids such as CSS, cerebral spinal fluid, that have a much longer T1 than any other tissues that we typically image. And this can be thought of as kind of an add-on contrast, in fact. You can combine it with different TRs and a little bit of flexibility in the TR, and then different TEs as well to, for example, get T2 weighting and flare. So this brain example here, the image on the left is sort of a typical T2 weighted image where you have very bright signal from the cerebral spinal fluid. The image on the right is where there's a TI inversion time of 2.5 seconds, a very long time to null out the signal from the cerebral spinal fluid. But we still maintain this T2 contrast between the gray and white matter. And actually then you can see these, what I believe are called periventricular lesions, these bright signals around the ventricles that were kind of harder to distinguish from the surrounding fluid without this flare method to suppress the fluid signals. Okay, so that's it. Again, you should be able to go through and talk about saturation recovery, partial saturation recovery, and inversion recovery in terms of the contrast, how to draw a simple pulse sequence diagram, the evolution of the net magnetization, which we boil down to some of the equations that are shown. Great, thank you for watching.